The last part of section 8.2 is about what happens when you get two eigenvalues that are complex conjugates. And in that case, you basically start the same way that you normally would, where you would take one of these, either the alpha plus beta I or the alpha minus beta I, get an eigenvector that goes along with that eigenvalue, and then there are a couple of different options from there. One is this, which is by far the less conventional method, where if the bar over the top denotes conjugate, then whatever your eigenvector is that you get from lambda 1, it also has a conjugate. And if there are no other eigenvalues, your solution looks like this, where in the first term you say, oh, well, there's one eigenvalue and there's its eigenvector, and conjugate eigenvalue, conjugate eigenvector. So you could write it that way, but that would be like in chapter 4 when we had complex roots not using cosine and sine. It's the equivalent of that. So the more conventional thing to do there is to use cosine and sine. That's also the more conventional thing to do here. Although the way that you get there has got sort of an extra step. So let's see down here, where if lambda 1 is alpha plus beta I, and then that gives you eigenvector k1, then what you end up doing is that you can break k1 up into components. So you have a real part and an imaginary part. So that's what the RE and the IM are, just real and imaginary. Then the way that you can get the two linearly independent solutions, it's like this. So again, the B1 and the B2 are just pieces of K1, basically, right? Like the real piece and the imaginary piece. And then you can see the cosine and sine in there, right? Involving beta, just like it was in chapter 4. And then E being raised to the alpha times T, that also kind of looks like chapter 4. So it's a lot of those pieces that you use to get these two independent solutions, just that they're a little bit more involved this time, right? There's a little bit more going on back here in the brackets. But that's more or less what we're going to end up doing. With the first example, I suppose first things first, we'll get the eigenvalues. So determinant of a minus lambda I set equal to 0 is going to be our characteristic equation, just like it was before. You eventually get this as your characteristic equation, which does not have real roots. So I used the quadratic formula and I ended up with -1 plus or minus I. Then the next step, eigenvectors. So just pick one of these. So either -1 plus I or -1 minus I. Pick one of those eigenvalues. I picked -1 plus I. And then you would do what you would conventionally do. It's just that now you have a complex eigenvalue. So notice what I've got here. This is just a minus lambda I. It's just that lambda is -1 plus I, right? There it is. There it is being subtracted off on the diagonals. So you end up here when you simplify a little bit, and then you get this. I guess you rewrite those rows as equations, right? You're going to end up here with 2 minus I times k1 minus k2 equals 0, and then 5k1 plus -2 minus I times k2 equals 0. So here is another situation where you're going to have to pick a value that would work. So I just picked something easy, and I said, all right, well then if k1 equals 1, then that would mean k2 would have to be 2 minus I. That's going to solve the first one. And then just to double check and make sure that also solves the second one, I went through and subbed in. And yeah, considering that I squared is -1, this ends up working out and you get 0. So, okay, well then that means that k1, our eigenvector, we can write it like this, right? 1, 2 minus I. Or we can write it like this, where then here we've got it broken up with the real and imaginary parts explicitly written out. So there's the real part, right? The 1 and the 2. And then what's multiplied by I? Well, in that first component of the vector, nothing. So 0. And the second one, -1. So here's the real part of k1. Here's the imaginary part, which we're going to need, I guess, almost immediately when we get to the next page. So there I rewrote k1 again, where we've got it separated out here, the real part and the imaginary part. And then we said, on the first page, b1 is the real part, so it's just that 1, 2 vector. B2 is the imaginary part, so it's the 0, 1 vector. That's enough to put x1 and x2 together, because now we know what alpha and beta and b1 and b2 are. So we can say, okay, well then b1 is the 1, 2 vector, and then cosine of just t, because our eigenvalue that we're using is -1 plus I. So in that case, alpha is -1 and beta is +1. So just cosine t, and then minus, there's the b2 vector, times sine t, and then e to the alpha t, alpha is -1 here. Then x2 is pretty similar, right? The only difference is now you got the b2 at the beginning, b1 down there multiplied by sine, and this is a plus in the middle. But yeah, there's x2. And then the general solution, you can write it as c1 times x1 plus c2 times x2. So I just subbed in x1 and x2. Those are really big, the way that they're written out. But the things that are in parentheses, so like this piece here or this piece down here, you can rewrite those, right? You can simplify those because you could actually do the multiplication. So like this really is just a column vector, right? It's a column vector with 2 entries in it. So is this. So like this first one, I said, okay, in the first row, you're going to end up with cosine t times 1 plus sine t times 0. That's cosine t. Second row, cosine t times 2 minus sine t times -1. So it's 2 cosine t plus sine t. Right? So there it is, cleaned up a little bit. And then you can do the same thing with this one, where you can say, oh, this is 0 cosine t plus 1 sine t in the first row, minus cosine t plus 2 sine t in the second row, and I just wrote it in the opposite order, but it's the same thing. So that's a little bit cleaner looking, so I kind of prefer writing them like this just because it's not as drawn out. But this version up here, where it's not simplified all the way, it is also correct. So I guess either or, like whichever one feels like it's more of a final answer. Either one is okay. Different books would have different things in the back. Although I kind of lean toward the bottom one for aesthetic reasons, I guess. But either one would be fine. The second example, I stuck the solution in this time, and it's because the way that I would instinctively do this problem, I don't end up with that. I end up with something that looks a little bit different. And when I went through and did the homework problems out of our book, that kept happening. So I wanted to kind of manufacture that in the notes where that would happen as well, just to be like, look, if you do this slightly differently than whoever put the answer key together, you're going to get an answer that looks a little bit different. So that's what's going to happen here. So starting in the same place that we always do, get the eigenvalues first. So if we go through and do it, we get our characteristic equation, right? There's a minus lambda I, set that equal to 0. We end up eventually with lambda squared plus 1 equals 0, so lambda must be plus or minus I. Okay? Well then, in order to get the eigenvectors, I'm just going to start with I rather than negative I. I guess it wouldn't make much of a difference, but there's a minus little I times big I, right? Big I for identity matrix. You end up there. And then from here, I think you can just pick stuff, right? Because if you go from the bottom, this is already pretty straightforward, right? We've got k1 plus -2 minus I times k2. So if you say, well, then if you just let k2 equal 1, and then k1 be the negation of this, so 2 plus I, that should work. And then just to be safe, I checked the top as well, just subbing in 2 plus I for k1, 1 for k2, and yep, that works out. You do get 0 like you're supposed to, so that'll work. All right. Well, then big K1, our eigenvector, that can be written out as 2 plus I, 1. Or we can write it this way to separate it out, where we've got the real part and the imaginary part. So 2, 1 are the real parts, and the imaginary parts, we've got a 1 on the top because we've got that I. We've got no imaginary part in the bottom, so that's just a 0. All right. Well, then B1 is going to be the real part, just like it was before. B2 is going to be the imaginary part, so respectively 2, 1, and 1, 0. And then if we substitute in, right, there's B1. Once again, beta is going to be 1, right? Because the eigenvalue that we're using is I, so alpha is 0 and beta is 1 there. So just cosine t there, sine t there, and then same thing down there, cosine t, sine t, right? Other order, you got the b2 multiplied by cosine t down here and b1 over here and a plus instead of a minus. And then what we're multiplied by, we're out here where we've got the e to the alpha t. Alpha is 0. So this is just e to the 0, so it's 1. And so then that means that if you're going to write out the general solution, and I wrote it the cleaned up way, where I kind of cleaned up what's in the parentheses there and there, then in that first one, we're going to have as the first entry of that vector 2 cosine t minus sine t, and then the second entry underneath is just cosine t. And then doing the same thing here, right, we end up down there. This is not the answer that's on the last page. Right? The answer on the last page had 5s in it. So what happened? So my answer doesn't look like that. Why not? Because I used the second row of the matrix. So if I go back up just to point this out, in order to get k1, the eigenvector, I used the bottom row here. Right? I used k1 plus negative 2 minus I times k2 equals 0. If you pick the top instead of the bottom, so like if you used 2 minus I times k1 minus 5k2 equals 0, and then got an eigenvector from that, then you'll get this answer up here. But because I picked the bottom row because that looked easier to me just because I had a 1 in it, that's why I'm getting a different answer. So that's what this is about down here, where I didn't get the answer that was there on the previous page because I used the bottom row instead of the top row. That's okay to do. There's nothing wrong with it, but you will get an answer that looks a little bit different. So if you use the top row, you'll get that answer that's on the last page. And even though those answers look different, they are equivalent to each other. It's okay to have that happen. And I really wanted this to come up because I think this may happen to you with the homework. It happened to me more than once. So I really wanted to make sure this came in as kind of a disclaimer, like, look, this happens. There are parts where you just have to make a choice, and if you pick the other way, you're going to get an answer that looks different. So that is a possibility. So I just wanted everybody to be aware of that, because otherwise it does kind of look like you're doing things wrong with the homework when your answer doesn't look like the one in the back, even though that might just mean that you picked a different row when you got your eigenvector.